Nobody is playing this. No human at the keyboard. That's a program, reading the screen, deciding what to do, and pressing the keys. Every line appearing on the right is a decision it made. Both halves are the same run. No neural network. No training run. A few thousand lines of ordinary code. The interesting part isn't the game logic, it's the plumbing. The game is ADOM, Ancient Domains of Mystery, version 3.3.3. It was written for Linux. DOS was the port, not the destination. Thomas Biskup started writing it in July 1994 as a student in Witten, Germany. He gave it away. Not shareware, postcardware. If you enjoyed it, he asked you to mail him a postcard. He collected them. Then it never stopped. Steam, a graphical tile set, a Kickstarter. The build I'm automating is from 2019. Same game, 25 years apart. Here's the part that surprised me. That 2019 build is still a DOS program. Someone compiled it for an operating system that had been discontinued for the better part of 2 decades because some people still want to play it that way. It even ships with a second program beside it. Without that helper, DOS cannot address more than 1 megabyte of memory. That tells you exactly what kind of machine this thing still expects to find. You are the @sign. So is everyone else. It's the glyph for every humanoid, so the village healer is one too. Which one is you is a problem this bot has lost runs to. Letters are monsters, a lowercase z is a zombie, hashes are walls, a dot is floor, a slash is a door, a slash is also arrows on the floor. The manual lists it under both. One shape, 2 meanings, and the bot has to guess. Angle brackets are staircases. Square brackets and parentheses are armor and weapons. A % is food or a corpse. That's the whole game. 80 characters across, 25 down. No pixels anywhere, which sounds like it should make automation easy, and it does make it possible. But I'm running the shipped executable, unmodified. So the first problem isn't what the bot should do. It's how a modern program gets a single byte in or out. None of this is original. There's a whole tradition of writing bots for roguelikes, mostly for NetHack, which is ADOM's older and harsher cousin. The big two are TAEB, the Tactical Amulet Extraction Bot, and BotHack. TAEB is a framework people have been building NetHack bots on for years. BotHack came later, and in January 2015, a bot built on BotHack did something nobody had managed before. It played a complete game of NetHack, start to finish, no human input, and won. That's called an ascension. For a bot, it took roughly 20 years of people trying. How it was done is the interesting part. BotHack isn't clever machine learning. It's an explicit model of the game. It knows corpses rot. It knows which branch it's in. It tracks what it has identified. Someone sat down and wrote the knowledge in. There's a counterpoint that makes the story better. In 2020, researchers at Facebook AI released the NetHack learning environment, which turns NetHack into a training ground for AI agents. In 2021, they ran a competition around it. Dozens of teams, neural networks against handwritten bots. The handwritten bots won. Comfortably, the paper's own summary is that symbolic bots outperformed deep reinforcement learning by a large margin, and that no agent of any kind got close to winning the game. Writing the rules by hand, then, is not the naive option here. On this particular problem, it's the option that currently works. That's the tradition this project sits in, and it's why you won't see a training loop in this video. Broadly, there are 3 ways to make an old game talk to your code. 1. Read its memory. The emulator has the game's memory sitting in a buffer. Find the address where hit points live, read it directly. That's what cheat tools do. Precise, fast, brittle, and a great deal of reverse engineering with no source and no documentation. 2. Replace the game. Use an open source version or a decompiled port and call its functions directly. Excellent when it exists. For this game, it doesn't. 3. Play it like a person, read the screen, press keys, repeat. There's a choice inside that, and it's the one that matters. Option 1 never goes away. The memory is right there. Choosing not to read it is the real decision. If the bot only ever reads what a human can read, it can't accidentally cheat. And every bug it has becomes a bug about perception. It misread the screen. That's a kind of bug you can save to a file and test. Hold that thought. This is where my project and the NetHack bots part company. NetHack is open source. You can build it, attach over a terminal, play it on a public server. ADOM is none of that. No source, no terminal, no server. There is a file. Reading the screen and pressing keys isn't a stylistic choice here. It's the only door in the building. That leaves one obstacle. A DOS game's screen isn't a file you can open, and its keyboard isn't something you can write to. They only exist inside a PC that hasn't been manufactured in 30 years. I need something that can run that program and let me reach inside it while it does, which is where the next few minutes go. If you've run an old game in the last 20 years, you've probably used DOSBox. It emulates an early 90s PC, processor and sound card and screen and keyboard, so DOS software runs on a machine that no longer exists. DOSBox Staging is the actively maintained modern version, and it has added something that turns out to be perfect for this. A built-in web server. You switch it on with one line in the config file, and the emulator starts answering web requests about its own internal state. Sit with that for a second because it's a strange sentence. The emulated early 90s PC now has a web API. You can ask it questions over HTTP, the same way your phone talks to a weather service. The version I'm using is a fork called DOSBox Automation, which extends that API specifically for this kind of work. Reading the screen, injecting input, recording video. It also documents itself. While the emulator is running, you can open it in a browser and get a live list of everything it can do. About 40 endpoints, screenshots, memory reads, frame-accurate key events, even running scripts inside the emulator. I use a small handful of them. The first one gives me the screen. I ask for the text endpoint, and the emulator hands back the 80 by 25 character grid as one long string. Not a picture. Actual characters. No screenshots, no image recognition, no OCR. The @ sign in that string is the same @ sign your eyes see. That's the whole perception system. One web request, several thousand times per run, and what comes back is text the code can search with the same string functions you'd use on any other text. The second call presses keys. There's an endpoint where you post a string and the emulator types it. Send the digit 6, and the hero walks east. Send the letter E, and the eat menu opens. 2 calls. Read the screen, press a key. Everything else in this project is built on those two. Everything I've just described works on the first try. Then you run it for an hour, and you discover that the emulator is a machine, not a person, and the game was written for a person. Here are 4 things that cost me real debugging time. They're all specific, but the shape of them is what I want you to take away, because that shape shows up in every automation project I've ever worked on. The type this text endpoint doesn't inject characters. It works out which physical keys would produce those characters, and it does that using your computer's keyboard layout, not the emulated one. Letters and digits are fine. They're in the same place everywhere. Punctuation is not. It moves around between layouts. I sent the key that means go down the stairs, and the game opened the character sheet instead. On some layouts, that bug doesn't exist at all. On others, it is waiting for you. The fix is to stop asking for characters and start asking for keys. There's a second endpoint that takes raw key events. Press this physical key, hold Shift, release. That skips the layout translation entirely. Going downstairs is no longer a character at all. It's a shift. One particular key named by where it sits on the board, and a release. Ugly? Yes. Layout proof? Also yes. DOS games do a thing where, after drawing certain screens, they flush the keyboard buffer. They empty out anything typed while they were busy. That's perfectly reasonable when a human is at the keyboard. It means a key arriving at the wrong millisecond is silently discarded. No error. Nothing. Which is why you cannot write this bot as a script. You can't write press P, then press R, then press space and expect it to work, because step 2 will occasionally vanish, and every step after it is now wrong. What you write instead is a loop that never assumes. Look at the screen, decide one thing, press it, look at the screen again. Did it change? If not, press the same thing again. Every action has to be safe to repeat, because it will get repeated. That one constraint shapes the entire architecture. It's also the reason the earlier version of this tooling, which was a script, got deleted. On startup, this build shows an advertising screen with an exit option in the footer, something like press it to exit. The letter changes every time you launch the game. There's no hard coding that. The bot has to read the footer, find the letter in the brackets, and press it. Which sounds trivial and is, but only if you already assumed the screen is data to be parsed rather than a fixed thing you memorized. Write down press a, and you have a bot that works 4 times out of 5, and a day of your life gone finding out why. Some commands are 2 keys. If the game eats the first key and keeps the second, You don't get "nothing happened." You get a completely different command. The press it again strategy cannot undo that, because as far as the loop can tell, something definitely happened. The fix is to send both keys as a single scheduled sequence with millisecond timings, so the emulator delivers them as one unit. Either the game gets the whole command, or it gets none of it, never half. None of those four are hard, once you know. All four are invisible until they bite you. That's automation. I said the bot only reads what a human reads. There's an asterisk on that. The text endpoint gives you the characters and throws away the colors. But the game uses color to mean things. An altar's color tells you which god it belongs to, and one symbol means both a ring on the floor and deep water, separated only by color. That one matters. Walking into deep water in this game will drown you. So for those questions, the bot gets the color another way. When request 2 bytes at the address where the PC's text screen has lived since the early 80s, it reads the color of a character it can already see, and that's why the word sheet is in quotation marks. A person playing this game is looking at those colors. Nothing here learns anything a player doesn't know. What's unusual is the root, and only because the convenient endpoint drops half of what's on screen. The line I actually drew is somewhere else. The bot may ask the emulator about the display. Anything genuinely on screen in front of a human player. It may not ask the game about the game. No hit points read out of memory. No peeking at the level layout. Cross that line and you stop building a thing that plays the game. You start building a thing that inspects a program. Here's the decision side, at high altitude. Every 400 milliseconds, the same 5 things happen in the same order. Read. 1 request for the screen. Understand. 1 layer turns that text into meaning. Where am I? Where are the monsters? What did the game just say to me? This is the only code in the project allowed to look at raw screen text. Everything above it works with facts instead of strings. Remember, the game shows you one screen. A player carries a map in their head. So there's a memory layer that merges each new screen into a remembered floor plan, tracks which corners haven't been visited, remembers where the stairs were, and notes things like, I bumped into a wall there, so that wasn't a floor tile after all. Decide. This is the brain, and it has 3 tiers. First, reflexes. Is something about to kill me? Retreat back into a corridor. Shoot the thing before it reaches me. Anything urgent wins immediately. If nothing is urgent, plans, a priority list. Am I starving? Am I carrying too much? Is there better equipment on the floor? Is there unexplored map left? Should I take the stairs down? First one that applies wins. Then rules that can say no. A veto layer, sitting between deciding and acting, that cancels moves which are always wrong no matter how good an idea they looked. Don't shoot something you haven't identified. Don't step onto that kind of altar. Don't back yourself into a corner you can't leave. Act. The last layer turns walk east into keystrokes, and it's the only code in the project that touches the keyboard, which is where all 4 of those gotchas live, sealed off in one place. That split, 1 layer reading and 1 layer writing with nothing but functions in between, is the payoff for the decision I flagged earlier. Because the brain never touches the network, I can save a screen to a file, hand it to the brain offline with no emulator running at all, and check what it decides. The test suite is a folder of literal saved screens from real runs. Every crash this bot has ever had is now a file in that folder and a test that says, given this exact screen, don't do that again. Results, honestly. It doesn't win. It isn't close to winning. It dies, usually somewhere in the first handful of dungeon levels, to something a competent human would have walked around. Watching how it fails is the entire hobby, though. A bot's failures are wonderfully specific. It once picked up an item, decided the item was too heavy, dropped it, and then, a few seconds later, spotted something valuable on the floor and picked up the exact same thing. Forever. It has stood in a fight against a monster whose touch destroys equipment until it had no equipment left because nothing in it knew that particular monster was a special case. It has ridden one staircase up and down 7 times in 15 seconds because 2 different parts of it wanted to be on 2 different floors. Every one of those is a rule that didn't exist yet, and the fix is never train it more. The fix is a person watching a recording, working out what the bot believed, and writing down the thing it didn't know. Corpse rot. That symbol is sometimes water. You cannot leave this area while something is standing next to you. That's what the NetHack people spent 20 years doing before one of their bots finally won. Not tuning a model. Accumulating knowledge. One specific, stupid, hard-won fact at a time. That's the shape of it then. An emulator that answers web requests. A screen you read as text instead of pixels. Keys that go out as physical key events, because character encoding is a lie. A loop that assumes every single thing it does might silently fail. And on top of all that, a pile of rules written by someone who kept losing. If you want to try this yourself, the ingredients are free. DOSBox Staging with the web server switched on, any DOS game you like, and about 50 lines of code to read the screen and press a key. That part takes an evening. The rest takes as long as you want to give it. Thanks for watching.